All right. So welcome to my channel, Beyond the Code. And in this, I guess, tutorial series, I'm going to be covering problems that I think are relevant to general engineering problems um, in the using the finite element method. So let's get started. So the problem we're going to look at today is a principle of minimal potential energy. And what we're going to do is we're going to look at a bar problem with a variable, uh, a var with a shape function to the bar. And what we're going to do, excuse me, is we're going to solve a problem. So suppose we have a bar. Some some length L, and the bar has a shape function of a of x is equal to a naught plus um, a naught times x over L. So what we want to do is now derive the stiffness matrix of this bar. So first of all, what we got to do is step one. We follow the finite element method. We need to discretize this bar into elements and nodes. So we have node 1, 2, 3, and element 1 and 2. So what we have to do is then in step two is first define our energy function. So we're going to say the energy in the bar, U, is equal to 1/2 times the integral of EA of x du dx squared dx. And so because we do not have any parameters and we want to solve for the stiffness matrix, we really have to use this term right here to define or to utilize our shape functions. So in this case, we have a second order equation, and based off our boundary conditions, we'll say 2m minus 1 is equal to 2. Therefore, m is equal to 3 over 2. And what we're going to do is we're going to apply Gauss integration points, and we're going to apply two integration points. So based off of the theory, we know that for two Gauss integration points, we have 1 over L and negative 1 over L. And so the way it works is when we use shape functions and weights, we say that the sum of weights, so f of x, is equal to the sum of the weights times the function. And what we do is we substitute du over dx for the sum of the weight function. So next step, step 3, what we want to do is we want to substitute du over dx squared for our Gauss integration points. So bring them back into the equation. U is equal to 1/2 is the integral of E a of x du over dx squared dx, which becomes E a naught times 1 plus x over L. Okay, I guess we'll bring this on the integrations here. 1/2. And then du over dx squared turns into negative 1 over L u1 plus 1 over L u2 dx squared. Okay? Now, what we want to do is we want to evaluate the integral and reduce the function. So we'll say E a naught over 2 times the integral of 1 plus x over L. And what we really want to do is isolate the 1 plus x over L, but first what we want to do is take care of our displacement term. So we'll say u2 minus u1 over L squared dx. And so now that we have this, we can then evaluate the integral and reduce the bar problem. So we have E A naught over 2 times U2 minus U1 over L squared times the integral of L1 plus x over L. Now that we have this, we want to evaluate the terms. And so what we end up with from 0 to L, my mistake, is we get x plus x squared over L over 2L evaluated from 0 to L. And what this leaves us with is 3L over 2. Now we bring it back into this term, E A naught over 2 times U2 minus U1 over L squared times 3L over 2. And when we combine all the terms, we say the minimum energy in the system is E A naught, or 3 E A naught. Is that right? 2, oh, yeah, 2L. Checking the math. 3L over 2. Yeah, 3A naught over, whoop, pen just died. Mercy. 3A naught over 4L, U2 minus U1 squared, and that is our final expression. So when we want to find the actual stiffness matrix of the bar, we get stiffness matrix K is equal to 3E A naught over 4L 1, 1, negative 1, negative 1. And this here is our final answer. All right. Hope you guys liked the video. If you want to see some more or have some problems you want me to solve, just like and subscribe.